In this lesson, we will learn how to graph polynomial functions. We begin by looking at some of the basic functions and their graphs. One of these is f of x equal to x squared. This is a monomial, a quadratic function actually, and the graph of this function is given by this parabola here. And f of x, which is equal to x cubed, has a graph that looks like this. So to help us graph a polynomial function, we have to look at the leading term of the polynomial function. The leading term will tell us the degree of the polynomial. So when looking at the degree of the polynomial, all you need to do is look at the terms, and the one that has the highest degree or the highest exponent is the leading term. So if, for instance, n is the leading term, we'll get that and examine that, and through that we will be able to identify the end behavior of the polynomial function. So first, look at the coefficient of the leading term a sub n. Now, if a sub n is positive, that's greater than 0, the end behavior of the function is going to look like this if n is odd. So if n is odd, the left end tail of the function goes down and the right end tail goes up. And also, if it is even, if n is even, if the degree is even, say 2, 4, 6, 8, 10, both end behavior of the polynomial function will be in that same direction. They're both up if a sub n is positive. Now, if a sub n is negative, the end behavior, the left end tail will be going up, and the right end tail will be going down. And if it is even, if the degree is even, both of the endpoints will be in the downward direction. So to help us remember this, we can remember it like this. If n is odd, if the degree is odd, and if the degree is odd, the end behavior will be opposite at each other. And if the degree is even, the end behavior will be the same at each end. And so to help us remember that, it would be helpful to remember the graph of the basic functions that we just saw, namely the graph of f of x equal to x squared, this quadratic function. This is an example wherein the degree is even. So if the degree of even, we know that in this case here, the graph would look like this. The endpoint will be in the same behavior, at the end. They're both going upwards. Because also it's important that to note that the coefficient of x squared in this case is 1, which is positive. And also remember the graph for f of x equal to x cubed. This is an example of the graph of a polynomial function whose degree is odd. Notice that in this function here, the end behavior are different. So one is going down, pointing down, and the other one is pointing upward. Now let's consider the following examples here. Determine the end behavior of the graph of the given polynomial function. To do this, we are going to look at the leading term, that is the one with the highest exponent. In this case, it is equal to negative 3x cubed. X to the 7th. Now, in the leading term, the coefficient here, is negative 3, so that is less than 0. And the exponent here is positive 7, which is odd. So we have the a here, our a sub n is equal to -3, and in this case we know that is negative, and the degree is 7, and that is odd. Now, we've seen that if the degree is an odd number, so if the degree is an odd number and the coefficient is negative, the end behavior would look like this. So they have opposite behavior at each end. And note that the first one, the left tail is going up and the right tail is going down. So the end behavior would look like this. Example number 2. Determine the end behavior of the graph of the given polynomial function. Now, this polynomial function is not written in its standard form, but we can still get the leading term by multiplying this expression and this raised to this power and this x here raised to that power. And so the leading term would be x times x squared times x cubed, and that gives us x to the, there's a 1 here, 1 plus 2, that's 3, plus 3 is 6, x to the 6. Now, the coefficient of x to the 6 is our a sub n, and that is equal to 1, which in this case is greater than 0, positive. And the degree of the leading term is equal to 6, and that is an even number. Now, we know from our previous discussion that if the degree is even, going back here, if the degree is even, we have the same behavior at each end. Both of them, either both of them is pointing upwards or both of them is pointing downwards. And that depends on the sign for a sub n. In this case, we have a sub n that is greater than 0. So therefore, the end behavior would look like this. And so the end behavior is both pointing upwards. Also, it is helpful for us to look at some properties of polynomial. We have learned how to identify the degree of the polynomial function. From the degree of the polynomial function, that also gives us the idea of the number of peaks and valleys, or the number of turning points. And the formula for that is just equal to the degree minus 1. So the degree minus 1 is the number of turning points, or that's the maximum number of peaks and valleys. And then you can also get the maximum number of x-intercepts. The maximum number of x-intercepts is just equal to the degree of the polynomial. So let's take a look at this example here. For the first one, the leading term is x cubed. By looking at the leading term, we say that the degree of this polynomial function is 3, and then the maximum number of peaks and valleys is 2, and the maximum number of x-intercepts is 3. So we use a maximum number because it doesn't always, the number of x-intercept does not always equal to the degree of the polynomial. So one polynomial that we already discussed is a quadratic function. We have seen that a quadratic function, the degree of a quadratic function is 2, and we've seen that the x-intercepts could either be 2 or 0. Or you could also have 1 if the intersection, or if the vertex of the parabola is on the x-axis. So that is the number, so that means that the number of, or the maximum number of x-intercepts is equal to the degree of the polynomial. Now let's take a look at this second example here, x to the 5th. So for x to the 5th, the degree of that polynomial function is 5 because the exponent is 5. That's the highest exponent in the term here. The leading term is the one with the highest exponent. And therefore, the number of peaks and valleys is equal to 4. That's degree minus 1. And then the maximum number of x-intercept is also equal to 5, the degree of the polynomial. Now let me emphasize this. The peaks and valleys is sometimes called the turning points in the graph. That means that the maximum number of turning points in the graph is just equal to the degree minus 1. Then now let's take a look at the third function here. For the third function, the leading term is negative x to the 6th. Therefore, the degree of this polynomial function is equal to 6. The number of turning points, or maximum number of turning points rather, is equal to 5. And the maximum number of x-intercepts is 6. For the last example, to get the leading term, we need to multiply this times x to the raised to this power here, and this x here raised to this power here. So therefore, we have x times x squared times x cubed, and that gives us x to the 6 as our leading term. The degree is 6. Maximum number of turning points is 5, and the maximum number of x-intercepts is 6. The next step in graphing a polynomial function is to identify the x-intercepts or zeros of the polynomial. You can do this by setting f of x equal to 0 and then solving for x. Those values of x are called the zeros of the functions. They're actually the x-intercept of the polynomial. And sometimes they're also called the roots or the solution of the polynomial equation, which is f of x equal to 0. Now, each root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. So the zeros, the roots, or solutions, they all mean the same thing. They are the x-intercepts of the polynomial function. Now let's consider the following examples here. Find all the zeros of the given polynomial functions here. To do that, we will just going to equate f of x. We will just make this f of x equal to 0. So we have 0 is equal to x times x minus 4 squared times x plus 5 cubed. Now, since they're all being multiplied to each other, we know that this will be 0 if one of the factors is equal to 0. That is when x is equal to 0, or x minus 4 squared is equal to 0, or x plus 5 cubed is equal to 0. Now, if x minus 4 squared is equal to 0, then that implies that x minus 4 is equal to 0, and so therefore x is equal to 4. Similarly, if x plus 5 cubed is equal to 0, that means that x plus 5 is equal to 0, and that x is equal to negative 5. And now for example number 4, we have f of x equal to x cubed minus 3x squared plus 256x. To find the zeros, we just have to let this be equal to 0. That is, we have x cubed minus 32x squared plus 256x is equal to 0. We can solve for x by factoring this expression here. So since by looking at each term here, we notice that x is a common factor. So we factor that out. We have x, and then we have x squared minus 32x plus 256 equal to 0. And then we will factor out this quadratic expression here. Notice that this is just a perfect square trinomial. This is equal to x minus 16 squared. And then copy x. That's equal to 0. Now, since this factor or product here is equal to 0, that means each of the factors, one of the factors here is equal to 0 if the product is equal to 0. So that is x equals 0, or x minus 16 squared is equal to 0. And that implies that x minus 16 is 0. So if x minus 16 is 0, x is equal to 16. These are the zeros of the polynomial functions. For the third functions, these are the zeros. For example, number 3. Now, after you have determined the x-intercepts of your polynomial function, the next step is to arrange those x-intercepts on a number line and then complete this table. This would help us get the different information that we need to graph our polynomial function. So we begin by identifying the x-intercept of this given polynomial function here. That is just, the x-intercepts are just 0, 4, and then negative 5. Those are the values when you equate each of this factor here to 0. And then arrange these numbers on the number line. We have negative 5, so from smallest to largest. So 0 and then 4. And from there, we can get the intervals. So each of this one divides the number line into several intervals. We have negative infinity to negative 5, negative 5 to 0, 0 to 4, and then 4 up to positive infinity. Then after that, you get a test number. Just pick a number within the given intervals here. So for this interval here, I would say pick negative 6. And then in here, I will pick negative 1. In this interval, I will pick a test value equal to 1. And in this interval here, I would pick 5. Then, after what I do next is to plug in each of these test number onto the given function to get the value of f of x. So I'm just interested in finding the value of f of x. So you can use your calculator to do so. And now plugging in each of the test number here onto this function here using your calculator, you will get 600 for negative 6. For negative 1 is negative 1,600. For positive 1, you get 1,944. Again, that is the value that you will get if you replace x here by this value here. Now replacing the x says here by 5 and then evaluating this polynomial function or getting the value at f of 5, you get 5,000. Then after that, you take a look at the signs. You're just interested in the sign. So this one is positive. This is negative, positive, positive. These are the signs. And then the graph would look like, so if this one, these are the x-intercept, that means this is above the x-axis. And this one is below the x-axis, above the x-axis, and above the x-axis. So you would just say above x-axis, and then this is below x-axis, above, and then below x-axis. Now we will find the y-intercept. So our function given is f of x is equal to x times x minus 4 squared times x plus 5 cubed. So to find the y-intercept, we're just going to replace x's here by 0, and then we will solve for y. So if x is equal to 0, we have 0 times 0 minus 4 squared times 0 plus 5 cubed. Now, regardless of what the answer here, you have 0 here already. So 0 times whatever number here is equal to 0. So therefore, the y-intercept is the point 0, 0. Now, lastly, let's graph the following function. So to graph the function, we are going to start first with the different intercepts. So let's have the y-intercept, that's 0, 0 as our y-intercept. Let's go back to the previous slides and see what our other intercepts. So the other intercepts are x equals 0. That was already covered for the y-intercept. And then the other ones are 4 and negative 5. So we have here 4 and then negative 5. Then we can refer to this table here. Now from the interval, negative infinity to negative 5. So on this side of the graph of the function is above the x-axis. And then between negative 5 to 0, it is below the x-axis. And above the x-axis for 0 to 4. And then for the interval 4 to positive infinity, it's below the x-axis. So we have here above the x-axis, the part here of the graph is above the x-axis. Now for this one between negative 5 to 0, it's below the x-axis. Now it's also important to take note or look at the given function here. Since the 0 x equals negative 5 has multiplicity 3, since the power here is 3, we know that the graph would cross the x-axis and would somehow curve in that. So if you recall the graph of x cubed, we know that it forms like a letter S on that part of the 0 or the intercept. So somehow it would look like this. So the curve would look like that. And then it would probably turn back to the point here. Okay, so that's the rough sketch of the graph. Okay, well, let me just fix that. So it would be like letter S. After that, it would be like that, and maybe curve back there. Then between 0 to 4 is above the x-axis. That's based on the table here. And then below the x-axis, beyond 4. So above the x-axis, we have this one. This one is not drawn to scale, so it might be a little bit farther up. Okay, so, and then after this would be, so this one at 4, we know that it would not cross, it will not go down here because the power here or the multiplicity is even. So that means that it will just bounce off the x-intercept. So after that, it would like curve up again. So this is how the rough sketch of the polynomial function would look like.